So it's getting recorded, right?
Yes, yes.
So our first question is like we need to search in a BST. They are given a root of a BST and a value, and we are supposed to find the node in that BST. And if the node, we are supposed to find the node in the BST which should be equals to the node's value. Return the subtree rooted with that node, and if you don't find, return null. So here it's like 2 is matching with this 3, so entire the root of this subtree should be returned. And yeah, if you want to search for 5, then you don't have any node with 5, so yeah, you'll return null in that case. And note that empty tree is represented by null, therefore you would see the expected. Okay, yeah. So what would be the brute force way?
So this is a binary search tree.
Yeah.
Okay. So I'm not sure. Do we really have a brute force way of doing it or not? But just do the binary search because we know the binary search tree property, right?
Exactly, yeah.
Yeah. So we can just use that and either find it recursively or maybe iteratively. You know. So that is what my
Recursive
thoughts are.
more time, I think, compared to iterative.
You are saying recursive might take more time?
Yeah, yeah, yeah. Because
Mm-hmm.
yeah,
Yeah, that might be a possibility. Yeah, because we are using a call stack, and
exactly. That is that, yeah.
if the tree is big or maybe a skewed tree, then it might affect the performance. That is correct.
Yeah.
So, or else you have a way of doing iteratively also, right? Yeah.
Exactly, yeah.
Yeah, so it
So
looks pretty straightforward, right? Either you do it iteratively, when you're doing iteratively, you just find what is the value you want to reach, compare that value with the root, and accordingly just move to the left or right based on the root's value and the target value, correct?
yeah.
And at the end, if you don't find it, return null or whatever he says.
Null, yeah, yeah,
Yeah, null.
yeah.
Or else return the node. So if you
Yeah,
return the node, you'll be returning the subtree rooted at that node, right?
exactly. 2, 1, 3 would be returned.
Right.
So reference of that node you are returning, right?
Right, the reference of the node.
Yeah. Do you want to share code type?
No, actually, you can go ahead. Actually, I did only the recursive way. So, yeah.
So this is a recursive way. Like if you don't have a root, you will return null. I mean, and if you face that root dot value equal to your val, then just return from there. I mean, return the root from there itself. And if value is greater, go. I mean, if the value is greater, definitely you'll go on left side. And if it is lesser, you'll go on right side. So this is the recursive call stack, right? Recursive one.
Right.
Yeah. It's like straightforward. I mean, self-explanatory.
Correct, yeah.
One question. So initially you were saying that iterative approach would take more time. Why? Because that would also be login.
Iterative would take lesser time, I think.
He said the reverse way, actually, yeah.
So
This
I believe even if tree is skewed, that means every time you will just look into one branch, and so if it is skewed, that means I mean it will take time, but we can't compare any difference between recursive approach or the iterative approach.
but in recursive, you would be using implicit stack, like call stack, right? That won't take some time extra compared to
So
the iterative.
so in iterative also you have to keep some stack, right?
No, I did. Is it? I did it like this, like as long as your root is not null. If the value matches, just return the root. And if your root dot value is greater than your the val, then you will go to the left side of a tree, or
I
you will
got it. Now got it. Yeah, you're right. So, but in the DFS, in the recursive approach, you are keeping it on the stack. Yeah.
Yeah.
So
if
yeah,
you-
you can avoid some allocations if you go with iterative approach, right?
Right. We'll have some small savings there. Yeah,
But there
absolutely
will
right.
be constant. I mean, that will be small constant, but yeah, definitely it will be slightly
Yeah,
better.
slightly better. Yeah, that's correct.
I think the non-recursive one is very straightforward also.
Absolutely. Yeah.
Yeah, more intuitive.
Yeah. So I think this was a very easy problem for the lead code, correct, right? There's
yeah,
nothing much in this.
This is BFS, right? Sorry, DFS, right?
yeah, this is the, I mean, function name I've just written, like,
Yeah, yeah. All right. Okay, I got
yeah.
it.
So we can switch to next then, or
Yeah, yeah.
some chat is there, or
Okay,
Rajendra.
let me check.
Yeah, just now I pasted the simplest. So the non-recursive one is that simple, just one line.
Oh, yeah, yeah, that's good.
Yeah,
No,
I
ternary.
mean, if you are using the root, then you don't need the current. So your root, you replace the current with root, and that is just one line there.
Yeah,
Yeah.
this is much more simple. Yeah. Ternary makes it much more.
Mm.
Yeah, crisp, tight.
Yep.
Yeah,
Yeah.
exactly.
It's good implementation. Yep.
Yeah. Yeah, we can switch to next then,
Yeah.
or
Yeah. No problem.
Sure.
so next is like minimum. We have to find in a sorted array. So the array is sorted in a ascending order and is rotated at some pivot, which is not known to us before, and we are supposed to find the minimum element, and none of the duplicates will be there inside your array. So array is being rotated at array is being rotated at this 5, right? This is the pivot, and this is the minimum element in your this rotated sorted array, and here 0 is your rotated sorted array. Yeah. So what would be the brute force?
So in this, we just going to find the index, or are we returning the value?
We have to return the value,
Okay.
minimum element here.
Minimal. Okay.
Yeah.
And there are no duplicates.
Yeah.
Okay. There are no
That
duplicates, and yeah. Sorry.
duplicate will make it bit more complex, right? I mean, it will add complexity to problem.
Right. Right. Right.
Yeah.
Yeah. And we have such questions also in which duplicates are present, like.
Yeah. So for this actually it's more simpler than them.
Exactly. Yeah.
So
So
for brute force would be just do an O of n,
yeah,
look for
single.
each and every array, each and
Mhm.
every element of the array, and
Okay.
just compare any element with the previous one. Okay, if you find a reverse way, like during iteration, like the earlier element was greater than the current one, then you return
Okay.
that current value. Correct.
Yeah, yeah, yeah.
So that might be but it will be O of n.
Go off and yeah, single. Yeah.
Yeah, right. So, but being rotated one, it might be possible to use a binary search some way.
Yeah, because of sorted. Yeah.
Yeah.
So in
This
this, so yeah, go ahead.
this problem is discussed in CTCI,
Okay.
but I don't remember the implementation. Just wanted to share.
Oh yeah, that Gil Lekman, right?
Yeah, yeah.
Yeah. Okay. Okay.
Can I come in? Hello.
Yes. Yeah.
Yeah. So there is a monotone in this. So there is a monotonous function uh, in regards to this array. So if we can see that we can take a pivot element, either the first element or the last element, and in correspondence to the first element is, say if we take the first element as a pivot, so we see that there is the array can be divided into two halves, where one half is like from 0, 1, 2, everything is greater than 4. Sorry, less than 4. So the monotonous function is the function is elements being less than 4 and elements being greater than or equal to 4. So we can search through those answers which are less than 4, and we want the minimum of those elements. So it is the monotonous, the first element uh, which is extremely smaller than 4. So that is 0. So yeah,
Pivot you are making as 5 or 4 here.
4, we can take 4 as pivot.
So-
And
But how can, I mean, like 5 should have.
So no,
Because-
which example you are talking about? Is it 2 or 1?
uh,
Oh, the one which is shown here. Okay, sorry.
the second one, yeah, the second one,
Okay.
example 2.
So you are saying
Oh.
that you use a monotonic stack, huh?
No.
Uh-huh.
See, we can apply binary search on monotonous function also, right? The functions which give true for a while and then false for a while. So or false for a while and then true for a while.
Okay.
So
Mhm.
so if we take 4 as pivot,
Mhm.
4 is greater than equal to 4, 5 is greater than equal to 4, 6 is greater than equal to 4, and 7 is greater than equal to 4.
They're breaking like this. Sorry, I mean 0,
Right,
1, 2
right.
in this, right?
And then 0, 1, 2 is less than equal to 4. So we try to find those numbers which are less than equal to 4. So we'll get, for example, we got 2. Then that is our answer. That can be one of our answer. And then we are like looking for better answers. So we'll go for 1. And the best answer is 0. So it is the minimum of the elements which are less than 4. So binary search can be used to find optimization, used to solve optimization problems, right?
Yeah.
So usually we take, for example, binary search is being used in perfect square. So we see that in perfect square we try to find the uh, element which is the root, which is the element which is maximum and close to the square of it. You getting me? So optimization problems are being solved by binary search.
Okay, that's a very interesting. Can you just write it on a whiteboard so everything will be much better? Are you okay with that?
No, I'm not using a computer.
Okay, no problem.
Oh,
I was using
Okay,
my
the last one, yeah, the first one we got it. The last one you're talking about the square, right? Could you
Yeah.
elaborate slightly more if possible?
If you open the lead code perfect square question,
Mm. Okay, you want to go to a different
search it and
question.
open perfect square.
We want to do that. Maybe we can do that after the session,
No, I
right?
just want to explain that
Okay.
binary search over answers. I want to explain that
Okay.
thing.
Susan, can you do that, please?
Yeah. Sorry, no, sorry. I'm sorry. I'm sorry. Not perfect square. Square root. Square root. The question is square root. SQRT of X. Yeah, I'm sorry. Yeah. So yeah, so square root of 4, say square root of 36, we want, or square root of say 37. 37 will be more than 6. So the answer for this question will be 6. So 6 is the highest number, which the square of which is less than or equal to 36. So for example, 1 square is less than equal to 36. 2 square is less than equal to 36. 3 square is less than equal to 36. 4 square, 5 square, 6 square. But 7 square is greater than 36.
37.
So there is a monotonicity. You can see that from 1 to 6, all the squares of all the numbers is less than equal to 36. Yeah. So we want the last best answer. If the say, suppose the function is less than equal to 36, whatever number is given, less than equal to n. So 1 can be the answer, 2 can be the answer, 3 can be the answer, 4 can be the answer, 5 can be the answer, and 6 can be the answer. So our best answer is 6. So we are optimizing our answers. We want to find the optimal answer. In the discussion, you can search.
Okay. Yeah. So that similar thing you can apply over here. That is what you're trying to say, right? Yeah.
Yeah, exactly. There is a monotonic function, and using which so this is the way you discretely apply binary search over answers. Over answers, you can discretely apply binary search. So because say you got a mid and you were checking that it is the passing that mid to the function, the monotonous function, you are checking it is true or false. If you get a true, the left half of the answers are disregarded because you got an answer. So you can reduce your space. You can binary search over the answers, and at the end, with the answer which you are left with is the optimal answer. It can be the maximum or the minimum. It can be the last one of the answer or the first one of the answer, depending upon the question. If the question wants the minimum or the first one, or if the question wants the last of something or the maximum of something. So this is a discrete. This is very interesting. This binary search, because in maximum competitive questions, binary search is used this way only. Yeah, this was my two cents for
Yeah,
this.
it's good. So yeah, so in sorted one, you'll be applying binary search only on the two halves, right?
So the interesting part is you don't need the array to be sorted or anything, because you are binary searching over the answers, and answers are generally sorted. Answers are generally true for some cases and then false for some cases. So say for square root question, uh, for example, for 36, from 1 to 6, it is true that 1 to 6 is less than equal to the square of 1 to 6. From square of 1, square of 2, all are less than equal to 36. So it is true for the answers 1 to 6, and it is false for the answers above that. So you don't need arrays to be sorted, because if you are binary searching over answers, for example, today I was solving that question, find finding
Okay.
duplicate in that is also an interesting. That question is also an interesting application of binary search. All these are good applications of binary search. You can do this monotonic session once with all these questions.
Sure.
For that, you don't need the array to be sorted.
But yeah.
Open that question, the previous one which we were solving, that rotated minimum in the rotated.
Yeah, really good problem. Shashank. The one what we are working on. Find minimum in the rotated.
Number was
Okay, the number is 153.
So here the monotonic function is that everything from 4 to 7 is monotonic function is 4 being the pivot element. If we choose 4 as the pivot element, everything from 4 to 7 is greater than 4, the pivot element, and everything from 0 to 2 is less than or equal to less than 4. So we want the minimum of those answers which are less than 4. Minimum of those answers are first of all the answers are 0, 1 and 2, and the minimum of those answers is 0. So if we keep our low at index 0 and high at index nums.length minus 1, and we like binary search over the answers that so at the end we just have to reduce our search space by half every time, and at the end we will reach at 0.
okay.
Yeah, good.
So somebody wants to share the code, like?
No, actually, yeah,
Yeah, like
yeah. The way he was actually,
explaining. Yeah.
yeah, explaining with this, but yeah, that's a good way of doing it. But I was just thinking, how can we reduce the space by half? When you are at a midpoint, okay. I got the point what he's trying to say. If you have something, if you are like if at 4, so you have 0, 1, 2, 3, which is the area of our interest, right? So when we divide that into mid, so the first thing what we try to do is we try to reduce the problem space, right? So first we compare our mid with which element? So we
Immediate
compare,
previous.
okay, immediate, okay. So we just compare with the immediate first, the previous and the next, correct?
Yeah.
And if we don't find them, then we try to reduce it based on our comparison with either the 0th position or the least one, means the left side, or maybe the right side, right? Either of it. And then
Yeah.
try to, okay.
So instead of this comparing with the next or the previous one, can we compare it with the last element? Because if our mid is at somewhere like our mid is over here is 5, and we can compare it with the last, like which is 2, and if our element is mid is greater, then which means that our uh, that our
You have to move to
zero
right.
x would be on the right side, and that because I started implementing using the next and the previous, I face some issues over there. So I thought that approach is not as much suitable of. as we are.
Okay.
I don't know if someone has done this approach. Please share the code of this because my implementation was wrong, but I do want to see that.
Yeah, I think that's a very tricky implementation. But yeah, what Mudsil was saying was actually a great way of understanding that.
So he's not trying to find the pivot directly. He's applying binary search on the entire array, right?
Yeah, that is what I think Sonia is also saying, right? She says that compare
Yeah,
with
yeah,
either of
I
that.
was
Yeah.
also saying the same thing. Yes.
It would be good to, because I usually do the way what Shashank said, right? It's just compare the previous one or the next one. If you don't find it, then move on and then you try to reduce this problem space, by
Yeah.
comparing with either the left or the right. But as they are saying, you first do reduce the problem space and then you try to compare your elements.
I think once you do a mid, right? First, initially you just divide what is the pivot. Once you find the pivot of that entire sorted array, rotated sorted array, and then you can just look at the first and the last element. Based on that, you can decide which way to go. So that will also shorten one more. In this case, like 4, 5, 6, 7. So let's say your pivot is 7. Then you can always look at 7 and what is the end at that point, like 2 and 4. You get 2 endpoints, right? The starting point and the end point. And then since you know that 2 is on the right hand side, so pretty much you can neglect the 4 part because you know that your smallest element lies in between that 7 and 2. Basically, index 0, 1, 2, 3, and 7. That's how you can keep on moving. I think it's just a variation to binary search. It's like there is another variation in this where we say that what is the point or what is the index where the array has been rotated. It's the same question. It's just you have to find the minimum. We just have to give that point as an answer.
Right. It is almost the same question, yeah. But a slightly different way, yeah.
I think the catch is only just to when you have that condition where you say where to move to find, like if you are finding a number in a sorted array, find an element in a sorted array, it's the same thing. You just have to add 2 more conditions to this where you also check for the start and the end point so that you know where to go, where your element lies.
Yeah. Look, one optimization is like if you find the pivot element is lesser than right and lesser than left also, then that would be the minimum one always, right? You don't need to recurse further. Directly from there you'll return.
So that it would be one exit condition. That's
Exactly.
like, yeah, that would be one condition. But if our mid is like in between, which is like, for example, we have 3, 4, 5, 6, 7, and at the end we have only 0. So our mid would be like somewhere in 4 and 5. And we don't know that which pair. So we need to check so for example our mid is 4 and we have only 0 at the end, so we need to make sure which way we need to go because our previous and our next is also like a monotonous increasing thing.
You can actually, if you can compare with the last element, you will know, right, whether it will be a last or the first element. You will know whether it's whether you need to go on to the left or right.
Yeah, that's one of the thing which I thought would be best to compare.
Yeah, I tried the same way, like comparing with the last one. If it is last, come from the last end and you get the minimum.
So last, you mean to say the last of the array or the left or right? Because
Right.
Okay, the right. Okay.
So if you compare this 2 with the 4, so it will be always like if it is not sorted, if it is rotated based on the pivot, then it will be the 2 will be always less than 4. If it is not, then if it is sorted, then always this will be the minimum if it is sorted. So compared 0 to 7, 0 is the minimum of 7. So then just return 0. Otherwise, come back and look for these 3, which is the minimum.
Yeah, this is one we can do. Yep. So other one is if I have one particular case of all the Like I don't have any rotated thing.
Yeah.
Then
So in that case, you can just compare the start and the last element, right? Maybe it's a special case.
yes, okay, yeah.
Just do that
Then
before.
just return the start one. That would be
Right,
the
right.
one.
Yeah. Yeah, Shashank.
I just now applied what was being discussed, and I think I have got a solution. Can I share it?
Sure, sure.
So no, you can just. I'm pasting it in the this thing. So if you could present, okay.
Yeah, sure.
So I'm using that approach somebody was discussing, right? So take the first element. So imagine, so there is another easy problem which it reduces to. The easy problem was find the first bad version, right? So yeah, if you could, by the way, this is JavaScript.
Right, so, I mean,
Yeah, so it is simple binary search only. The only trick is line number 18. So everything else is just binary search. Low is starting with 1 because if the first one is the one which we are returning, I didn't put that condition. That is just one line condition. So for example, we can just, this is a special case. This is the special case. Other than that, start the low from 1 and the high from the last element, which is always, this is just simple binary search. Okay, so this thing should go before line number 13. 29 and 30 should go before line number 13. It is a bit verbose, but I think it makes our understanding clear. Okay, so what it is doing is, if at any condition, if there is nothing rotated, then the first element will be less than the last element. So return the first element. So that is the special case we are dealing on line number 13 and 14. Other than that, because we have already ruled out the case that the first, the 0th index is not going to be returned, we can start from the low 1 and high nums length minus 1. So then we start our normal binary search. While low is less than high, compute the mid. Then if the nums mid is less than num, so num is the first element, right? So I think somebody was discussing. So if just like monotony increasing thing, if so, there should be one point in the array where, I mean, from the beginning, everything will be bigger than the first element if it is rotated. And at some point, all the elements will become less than the first element. We need to find out the first of those set of elements.
Right.
So to do that, line number 20 is basically checking, are we at a place where the mid, whatever mid is pointing to, if it is less than the num, that means we are already in that group, already in the less group. But how do we detect the very first one in that? That is line number 21. If just the number towards my left is greater than equals to the number, that means I am the first element in this group. No?
I have one question, like why we are moving high to mid minus 1? Why don't we go with the high is equal to mid?
High becoming mid minus 1, low becoming mid plus 1. This is the normal binary search, right? So I'm just doing that.
But in these type of, I have like in 1 or 2 sessions there's discussion, like in these type of questions we focus on to move our array in one particular side. We are forcing our search to move at one particular site. So that's why we do.
No, actually, mid is not a qualified candidate, right? You already found. That's why you are moving either right or left. So you are discarding that mid and going ahead of mid in one case, and in the other case, you are going below the mid. Mid, you already found that it is not a good candidate, right? Otherwise, had it been the case, then you'll never go for these else statements. So you are deciding either to go on the right of mid or you go on the left of the mid. That's why mid minus plus one.
But here you are not taking care of the mid, right?
Yeah, here
Can I
not.
can
In general case, I was telling for binary search.
Yeah, so that's why here is not that.
Yeah, here is slightly different, right? Because we have two
It's-
different conditions. 20 will be considering the mid also, right?
Yeah.
Yeah, 20 is
Or maybe the 25, 26, either of it. So
So,
it has to fall somewhere, right?
so the way to see this implementation is, first of all, line number 13 to 14, it is a special casing. That's why it is not, the low is not starting from 0. Other than that, if you just omit line number 21 and the else clause at line number 22, you will see it is just simple vanilla binary search.
Okay.
Just these two lines being added there to see whether, if I am on the group which is less than the initial number, am I finding, is it the first point? If it is the first point, the one on to my left, which is mid minus 1, I'm explaining line number 21, the one to my left would be obviously greater than equals to now, the first number. So that is how I detect that I am the first in that, I'm first in this less group.
So you are taking
Shouldn't
care
it
of
be-
that over here. Okay.
Shouldn't it,
Yes.
shouldn't it just
I
be
think
greater,
it
not
will
equal?
be it will be easy to actually feed on the example on that.
He's saying just walk through any example. Yeah. That makes sense.
Okay. Let me see if I can just draw on the screen. Can I?
And I don't think we need the equal to sign in the line 21.
No, this is already, I have evaluated, it is already accepted. So
I'm saying without equal to also it would work.
where?
On line 21.
No, it may become equal actually. What if the point to the left is, so this situation will occur when it is rotated by only one place.
I think an example would help.
Okay. I don't know how to draw.
Annotate is there. You can use that directly. You can draw on my screen.
Okay. Yeah. Let me annotate. So okay, what is the one that we are using? What is the example that we are using here? Let me see if I can pull it out.
Maybe 4, 5, 6. Yeah. First one. Second one. Yeah. Okay.
The second one, right?
Yeah.
Okay, so let us take this. So so first condition is 13 to 14. So we know that. So think about this. If it was not rotated at all, if this one was not rotated at all, then how do I undo? Okay, if this were not rotated at all, then the line number 14, I'm starting from the beginning. Then line number 14 will satisfy. Okay. Could you please keep that open, Sasank? Oh, okay, that is nice. So, okay, if you could scroll a little bit up. So, which one are we discussing?
4, 5, 6, 7, 0, 1, 2.
Okay, so I mean, which part of the code that we are discussing primarily, or the whole
In that the while loop, yeah, the whole
okay,
while loop.
the while loop. Okay, yeah. Sometimes if you, sorry, who's presenting? Yeah, Sasank, could you please? Okay, that's fine. That's fine.
Now don't move, Shashank. Yeah, okay.
Okay, so I'm coming to the while loop. So while loop started with 4. So imagine like this. So 4 is, this is basically 0. This is 1 more. This is 2 more. this is 3 more. Okay, and all of a sudden we see these guys are 4 less. Oh, how do we do? This guy is 3 less, this guy is 2 less. Okay, so distinctly there is basically, this is the group of elements which are our target. And what is the actual answer? The answer is whoever is the first in that list. Getting my point?
Yeah.
Okay, so because we took 4 as pivot, which is our pivot is norm 0. So this is our pivot. So whenever we check, we basically say wherever we are, norms mid, wherever we are we less than the pivot? If we are less than the pivot, we are in this group. Otherwise, we are here. With me?
Yep.
Okay.
So what is a pivot element 7?
This is pivot. This guy is pivot.
4.
Okay, 4 you are making it as pivot.
We don't know whether it is 4 or anything. We are basically taking the first element as pivot.
Okay.
So that way, basically, so the idea of pivot is to get this partition. So there are bunch of statement numbers which are higher, bunch which are lower. Okay.
Yeah.
So if we are in this lower group, which is this, if we are in this lower group, this lower group, then we want to find out the first of it. And the first has this characteristic that the one on the left will be always higher than the pivot. That is what we are checking here. With me?
Yep.
Other than that, it is just simple from here to here. It is just simple binary search, as you can see.
Okay, so for example, our mid is 7, and then it will not go to that if condition, it will go to the else condition and simply.
Right. So the low will come. Yeah, the low will come obviously here.
Yeah, 0. Correct.
Yes. And it will obviously converge. Correct.
Yeah, this solution is fine.
Yeah, this is kind of because it's built on top of the existing binary thing. It was pretty easy for me to understand. So I just did it this way. But the only thing is you'll have to take care of these extreme cases. These are the...
So 4 will come in place of 7, right?
Sorry?
4 will come in place of 7, right?
4 will come in place of 7? I'm not able to follow.
Like a pivot position.
Yeah, now when you actually do a mid, that time it will be 7, correct? Yeah. So on line 22, the first time you will get 7, nums mid. So 7 you are comparing with the num.
Yes.
Oh, okay.
Which is 4 and which is not true, so it will go to the else condition.
Yeah.
Else part. Yeah.
So in the line number 23, how did you get that intuition that if mid minus 1 is...
Very nice. That intuition is coming from, if you could, Sasank, if you could search for something called some build, failing build or fast failing build or something like that.
First bad version.
Fast bad version. Yeah. From that I got that intuition. Fast bad version. Bad. It is in lead code actually.
Bad, not bad.
Oh, lead code, it's a question on.
Yeah, it is a question in lead code. Fast bad version.
Okay.
So the intuition is, it is just an extension of this. So in the fast bad version, okay, got it. So in the first bad version, the question, it is an easy one. So it starts like this. What it says is, basically you have got n versions and at any given point if one goes bad, everything after that is bad. So what it says is this is good, then all of a sudden one becomes bad and everything else is bad. So the question here is, can you find the first bad version? So this thing is where you can simply say, okay, if the very first one is bad itself, suppose we are given things like this where everything is bad, then return this one. The first one is returned. Otherwise we have this situation. In this case we can do binary search. We can simply, wherever the mid points to, we can ask, hey, are you bad? If you are bad, we know that all towards your right is bad, but on your left, is there a good? If on the left there is a good, that means you are the first of this bunch. Otherwise, just keep going. So to answer your question, so the intuition was, this thing is also like this good and bad. If you consider the first number, the pivot number is, if you consider the pivot number is subtracted from the whole array, then you will see there will be some positives, and after that you will see negatives. So this bunch is the good version, this bunch is the bad version, and you will have to just find the first of this. That was the intuition.
Yeah, I think Mudassir was also explaining exactly the same, right? Almost similar. Yeah.
I'm not sure if I could explain better, but
no, this is correct actually. Yeah, it's perfect. Yeah, it makes sense. But I was saying, because we started with today on this problem, I think Mudassir was actually explaining the similar thing. Yeah, but yeah, that's good.
Okay. Yeah, Rajendra, one thing in that line number 21 and 22, I still think you don't need that equal to.
That equal to, okay, coming to the equal to, think about this. Suppose we are in
no, I think it's right. So in this problem may not be, because duplicates are not there, right?
Yeah, that thing.
No, what I'm saying is, suppose in this situation you are here, right? So pivot is this one.
Susan, could you switch to that window, please?
Okay. Let me clean first. Clear. Okay. If you could go there. Yeah, that is a very good question. That equals to, why it is required? 153. 153, the number. So let us think about a particular situation where, Sasank, if you could write, just remove 5, 6, 7 from line number 13.
From line number 5, 6, 7.
Yeah. Okay. So at this point of time, if you are at 0, okay, then on your left, it is becoming equals to. It is not greater.
I see.
Okay.
Okay.
So you're saying that
if you're already at the pivot.
Okay,
yeah,
you're already at the pivot.
Yes.
Right.
Yeah.
Yeah, so that's the corner case you have to take care of. That who you are. Okay. Yeah, that makes sense.
I mean, in binary search, always these corner cases are the haunting ones. They always trouble you.
Yeah, true.
That's why I always keep the binary search to very templatized, and just try to see if I can just do minimal work on top of that to get it right, because otherwise you'll get lost in all these simple corner cases.
Yeah, but that equal to sign was not an easy to get, Rajendra.
Yeah.
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 Okay.
So
That's true.
in binary search, we have three things playing, like the while condition and the changing of low and high. So I don't think there's a fixed one to like keep like our high as mid plus one or mid minus one. It depends on the question, right? Or is there something fixed?
No, it depends on the question. Like Sonia was saying, she has some example. Probably she has come across some example where the sometimes you can just play with this line number 25. Like if you want to keep it mid, but not mid minus one. There are some situations.
And most of the times it's redundant, but yeah, there's some situations where it fails.
Mhm.
Yeah, I think Pradeep raised his hand. He wants to say something.
Oh,
Pradeep?
sorry, not me. I'm not.
Okay, no problem.
Okay,
Yeah.
anyway, but I tried this implementation. Have you run, Rajendra, this implementation?
Yes,
Because
yes.
okay, because I did the copy and pasted, but it gave me some error.
Okay,
Not
so
error. Result was not nice.
probably you will have to also handle this single case. So there are few things I have. Okay, let me show you my complete code. It looks messy,
Okay,
so I
how
was
do I
ashamed to
remove
show
that?
it. Give me a second. I'll just put the whole code, and this is what is already verified. So it has passed all 146 these things. So this is the complete code. It looks messy, so I was not showing the whole thing. This is
Can you
JavaScript, by the way.
run this code once with that example?
Which example?
With that, the first example one, which means the 45670 with that example.
Okay, probably then I'll have to, I don't know. Do you want me to share the screen? Let me see if I can share my screen. Okay, where is the problems?
And guys, can you able to hear me? Satish?
Yeah.
Satish, I've gone through your code. By the way, I just want to make a change, I guess. If I'm wrong, I'm sorry for that. You have given high equal to high minus one. Actually, you should not give high equal to high minus one, right? You should give high equal to mid and whereas low equal to mid plus one. That is a concept of binary search, I guess. I guess that is the place where you're making mistake, I guess.
He's
Sorry,
talking.
I'm presenting, so whoever. So
Okay, I'm sorry, but I have gone through the code of Satish. Satish, the code which I've shared here in the chat box.
Right. Okay.
Oh, okay.
So you should give like a high equal to mid, because a binary search will split everything into half, right? So whenever the number of mid is less than or equal to number 5, we should make high value as mid. Else we should give low equal to mid plus 1, because we are splitting into every half. So I guess that is the place where you had some mistakes. Not necessarily though, right? Because if the mid is of no more use to us, then it's safe to make high as mid minus 1 and low as mid plus 1.
No, actually, if you refer to Satish's code, what is been shared on the chat, his implementation is slightly different. Yeah.
If you submit, Rajendra.
Yeah. So that might be something different to talk about. Yeah. Let's finish this, what Rajendra is talking about, then we'll go over that.
Yes, somebody asked me to run this.
Yeah, submit.
Oh, you want me to submit?
Yeah, I think okay, that's fine. I think you can
Yeah,
submit. That doesn't
it
take.
is already submitted.
Oh, okay.
So that's what I was saying. So this is submitted already.
Okay.
But I'm here.
Yeah. Okay, mine took. I did the other way around, which took very less time, which is coming from the end. This should have taken lesser time than mine, but anyway, lead code is very volatile in showing that calculating the time. Yeah.
Okay, I think we can continue.
I think just one point in calculation of mid. Why do we have to also use low again? Because usually it's just high minus low by 2, right? I joined a little bit late too, so sorry about that.
To avoid overflow, integer overflow.
Yeah. So if you have an integer value in C++, yeah, usually you'll encounter that.
Okay.
Yeah. Okay. So
yeah, we think.
yeah,
we can continue to the next one, probably.
I think there was a chat someone was talking about, right? About Satish. Is he there in the chat or he's left?
I think yes.
Satish is not there now. But I think what is in the chat actually he is doing a slightly different way. That code, I think someone was talking about, right? Yeah, both of them are not there.
No, I was it. Tamil. It's
Yeah,
me,
Tamil.
Tamil.
Yeah, Tamil. Yeah. So actually, it is different way of doing it. I think so. What you say makes sense to me also. Because you said the mid, right?
Yeah.
Because if you look at his mid, we are comparing with the high. Yeah, he says high is equal to high minus 1 and low is equal to low plus 1, right? When you're traversing the binary search tree. It should not be done that way because he's going one by one. But that is a one way of doing it also, I've found, because you can do this when you are in the very clear problem space, when you are in that place where you are actually having a dip.
Okay.
So there you can actually play with this, but I'm not sure whether he's doing it that way. Yeah, but I think, there might be
That
something to
looks to
look
me,
out for.
that looks to me not a binary search, right?
Yeah, that's not the way of.
That's a linear.
Kind of linear search.
Yeah, it looks like that. Yeah, but there might be some cases where when you are very close to that midpoint, you can use this. So somewhere
I
I've
think
seen that. Yeah.
that will work when you have a duplicate element in the array and array is rotated.
Yeah. Yep. No problem. So he's not there, but yeah, but that's a good thing you brought up. Yeah. Some different way of thinking about it. Yeah. Good. Thank you.
I mean, people have, I thought mid you can compare with previous element, and I didn't get the Rajendra's idea of comparing with num0 as such. I compared with previous element itself, and that looks straightforward for me. May not be for others.
Right. Yeah, I also did the same way. But this way, what he's trying to say is giving that example, right? The good and bad version of that. So if you compare with the version which is surely good, so you can clearly, so what you say, divide your problem into two, when you do binary search. So that is also a good thing to do, yeah, but it's a different approach. Yeah, so you can do it either way.
Yeah, so that saves one check, no? So if our low is starting from 1, then we don't have to check whether mid minus 1 exists or not.
Yeah.
I agree to what Uday said, the comparing both ends, but if we take the pivot to be the 0th index, then we are starting from the first index, so that check is saved.
Yeah, so it depends on what you are used to. That is what I would say.
Yeah.
Yeah, because binary search is always very tricky. It looks very easy, but it can be very complex. If you mess with the different conditions of it. Yeah.
I mean, in the loop itself, you could check whether there are only two elements or something like that. Two element or one element like that, and you could return that as well. If you are worried about the mid minus one.
Okay. Yeah.
Yeah, there can be many implementations.
Yeah.
Yeah. So we can start our last one. Like they have given an array of numbers which are sorted in ascending order, and we're supposed to find the starting and end position of the given target value. And it should make sure that should run in log n, and if it's not found, -1. So considering 8 over here, your first index is 3 and the last one is 4. and here about 6 you are not able to find star. I mean, the element itself is not inside the array, so -1 1, and constraints are this like nums is a non-decreasing, yeah, because they're already here. Either it increasing or some of the elements will be constant in that case. Okay, so what would be the brute force here?
So this is like today's session is all binary search.
Yes, yeah, exactly.
Okay. So brute force would be the straight away just go start from the first index, keep on looking for a target. As soon as you hit the target, you know store that index, and then you keep continuing because it's going to be a duplicate as what it says. In case if you don't find it also, then find the end index of the same target and then return. So it will be O of n times.
And regarding last index, yeah, we'll check the element, next element, if that is greater than target, right?
Yeah. So we'll have to find out a way where actually you can stop searching for the target. Yeah.
Yeah.
Or else do a binary search, correct? So for binary search, you find one index the same way, right? The lower index and the top index, and then you just store both the values and return. But just finding the lower index and upper index is a very complex procedure. That is, I would say.
Yeah.
I have done the previous one. It looks like we can use that approach twice here. Once from the making, I mean, it is a very bad approach, and this is just an intuition that is coming to my mind. One is to find the leftmost index. We can always use the existing approach that we already discussed. You start with 5 as the pivot and basically look for it. That way you will see, we'll get the leftmost index. And if we take 10 as index and just tweak that a little bit, then we'll get the rightmost index. But I'm sure it is not the good one to code.
But how do you find 10?
10 is the last element, right? Oh, you mean how do you find 10? 10 will, so again, special casing. When we are searching from left,
target plus 2? Like, no, sorry.
No,
Immediate target, try to find
actually,
target.
good question. No, my bad. Actually, that is a good
because
question.
it will be at any place, right?
Yeah. No, it is sorted, right? It is sorted.
Yeah, but the target might be very deep inside the array, right? And then you will have many values after that.
So immediate element is found greater than that. That 8 plus 1 9 is there, not. That will make sure that no, this element would be the. I mean, just one step before that would be the ending. Ending.
I think my intuition is not working here.
No, I think that would work, Rajendra, but the way you exactly did the solution, greater than or equal to, if you do it the reverse way, it might work, I would say. No?
I'm not sure yet. But...
Because that is the only way you do it, right? If you want to find the lower index, what would you do? You would just check for the greater than or equal to, correct? If mid with the target, if mid is greater than or equal to the target, then you keep on moving your left to the mid position.
Right.
So similarly, if you do for the other one, I would say.
Yeah, just to summarize, suppose I'm looking for 8 and I'm looking for the left end of 8. So we can simply see until we get 8. The first thing is to get into that range where we can find all 8s, right? Once we get in there, we don't stop there. We try to go towards left, basically until we find the situation where the the thing which is immediately to my left is smaller than me, right?
Yeah. Then if you find that, then you return the right in that case, correct? Because your left is already crossed, or no?
In a binary search, I always think of the middle pointer as the mid. So if my mid is already in the range of 8s, then I don't stop there because I'll have to get the first 8. So I'll continue until mid minus 1 is less than 8 or its index is 0.
Okay.
So that's how I find the left one. And for the right also, we can reuse the same thing. So go right, go right, go right until you find the, until it is the last element or the next element is bigger than me. But I have not coded it.
Okay.
So let's check whoever has coded it, if they could share it, then.
Shashank, right?
Yeah, I mean, the same approach I haven't used. That's like.
Okay. Yeah. Good.
Okay. So, I mean, like, I use just a normal binary search. Okay. This one. So what I'm doing, this is the position that will take care of first and last index. So for first index, I'm passing in the binary search the nums and the target, and it will go to this binary search. And this is a standard BS, like you have low and high, and as long as your low is less than high, I calculated the mid out of it, and it's checking if your nums of mid is greater than the equal to target. Then definitely your first position of that element will be your mid, right? Am I clear here?
Yeah,
So,
yeah, go ahead.
yeah. So first position, earlier it was the end of the string, correct?
Yeah, end of the array. Yeah.
And then you move. So you are just storing that position. So you would return it. Okay, good.
Yeah. Otherwise, I'll go to high is equal to mid minus one because mid was not the potential candidate. So in this case, what you'll do, you'll shift to the right side, right? Oh, sorry, you'll shift to the left side.
Yeah, you'll
Like
go to
like
move to the left side. Yeah.
Or the other way around would be like you'd be shifting to the right side. This is for finding the first index. Now the same code I'll be using for finding the last index, but only a difference that I'll increase the target by 1, so that if 8 is there, I'll look for 9, right? Because if you see 9, that means definitely a step before you are what you say, you are getting 8, right?
Okay, but if you don't have 9 in your array, then it's going to
Yeah,
return.
you don't if you don't have 9.
I guess he has written the first position equal to length of num. So the last will be returning, I guess. In the line number 15.
50?
Yeah. If 9 is not there, it will return the length of the last
15,
element.
you have written first position length of nums, right?
Yeah, it is. Yeah.
No, he's updating also, right? In line number 19.
Yeah, he is returning that index where it would be, where it would have been. If it is, even if it is not there, he's returning that index where it would have been.
Yeah, I index immediately greater than 8 you will have, right?
Right.
I mean, let's say if we are not exactly looking whether that 9 is present or not. If even if it is not present, then the index where it would be, what you say, where the 8 will be present will be one less than that fictitious element, that 9, like that imaginary element, even if it's not present.
Yeah, so the next greater element.
Yeah, so in
Yeah.
this case, the first example, it will move to 10, correct?
Yeah.
Okay.
So as 10 is greater than or equal to target, first position might change.
Yeah. Yeah. So 19, he will reach 19 anyway. Yeah. Okay.
I was thinking of if we can just pass the another method by making that we are looking for the first index and we are looking for the last index. So I have done similar kind of like approach where we can look for, like, we can iterate this binary search by just focusing on the first index and the last index.
Yeah.
So I'll paste this and on the chat.
You can also share this, no problem.
Yeah.
You do want to discuss that? Yeah.
Okay, sure.
Okay. Okay. Yeah, sure.
Looks like the song solution was exactly like lower bound, finding the lower bound and upper bound.
Yeah, exactly.
Right. And he has used a single function, right? So that makes it more.
May I want to increase the font? If you don't.
Can you see the screen?
Oh, increase the
You'll have
font.
to increase the.
Is it better?
Yeah, that's fine.
Shashank, if the number 8 is not there in the array, then are you like
minus when return? I've taken return minus of -1 if those conditions, if the target itself is not inside the array.
Okay, so in the second example where you passed 9,
okay,
so 9 was not there in the array, right?
Oh yeah.
So what are you doing? Are you returning -1 or the the expected position of 9?
The expected position of 9. I mean, we are not actually looking for that 9 element, just we are looking for the index. Like, had the 9 been present, what would be the index?
Okay.
I think he's asking whether you are checking that low or high. I mean, that 8 is present in that array or not. I mean, at least for the last element, you are increasing the target +1, and it may not be there, and you are using it. But whether you are comparing that first index to that element or not, is asking that.
Okay.
I think
we'll have to revisit. We'll have to revisit Shashank's solution after this again.
I think he's checking that the first index should be less than the last index.
Okay. Okay, let's go for Sonia now. Yeah.
Yeah, that is the final sanity check. First is
Yeah.
less than equal to last image. Yeah.
Okay, can you hear me?
Yes.
Okay, so here what I use, like for example, here I am just looking for a 0th and a 1 index, because like the start and the end. So when I am just putting at the, when I am looking for the start, I'll make it this false. Like when I'm passing this method and making this Boolean thing that I'm not looking for the last one, I'm looking for the first one. And here is one Boolean is like, this is simple binary search. And if I get my mid, I'll return, my result would be the mid. But the only check is here, if this is true, then it will be like, it will go at the end. Like I am making it biased by making it to go at the right side of my array. But here, if this is not true, then I'll be forcing it to go to the left, which means that the starting my move to my starting target. Is that?
Yeah.
So you are making it biased towards moving to the right or left based on your Boolean higher, correct?
Yes, exactly.
In case when you are the target is same.
Yeah, in case my target is same, I am making it biased. Rest is same, like if you didn't get the target, like either you need to go left or right, like a typical binary search for these conditions. The only check is over here. Like, and similarly, if I am making it true, like I am looking for the target at I am looking for the end of my end of the index of my target, then I am making it true, and I'm forcing it to go to the right side.
So you're looking for the upper index in this case.
Yeah, upper index, yeah. Here I'm forcing it to go to the left because I want my lower index. So I'm forcing it high to be the left part. And here I'm forcing my low would be the right part, because I'm looking for the upper index. So
Yeah.
these are the checks, and yeah, I've done this.
Low is equals to high. So when are you breaking? What are you returning?
So I'm returning over here the whatever the last I got the result.
And excuse me, I'm sorry for interrupting. Actually, here instead of giving bias directly, we can store, right? If num of mid equal to target, we can store the value of mid in result, and directly we can make the low value equal to mid plus 1. We don't want to go for high equal to mid minus 1. This will work, I guess, because here we don't want to go for bias. When I make the value of low equal to mid plus 1, automatically the while loop becomes false, right?
But the same function is being called for two different purposes to find the left index and right index.
Yeah.
I'm calling the same. Yeah.
So she's using it for the upper index and the lower index.
Mm-hmm.
It's a common function what she's done by making some minor tweaks. Yeah.
Can I see the main function once again? Sorry.
Sure.
Okay, even though if we call the same function, but that doesn't going to affect my array and target value, right? So it doesn't matter that we need to return false and true, because I'm going to call a function like search helper nums target. That's enough. And maybe this is enough, right? Because I don't want to make a bias over here.
Why?
The reason I'll be like, because searcher helper, I'll be passing these two arguments. That's enough. The entire array num and the target is enough. And when I go for, can you go for a result of zeros function? Sorry. Yeah. So when I go for result of 0 here, what I'll be calculating my first element, right? So when I'm calculating my first element, when I'm reaching the target, so whenever I'm reaching my target, I can make that high equal to mid minus 1. That's enough. When I make high, after storing the mid value in result, I can make my high value equal to mid minus 1. After that, I can say that the condition becomes false automatically. When I go for the next to while loop, the condition becomes false. I can return the value over here, return result. I mean,
so
the
where
value
you are saying condition becomes false, like this will become false.
Once after storing the mid value and result, I don't want to check this if else. Directly, I can store the value of high equal to mid minus 1. This is not enough. This is not necessary, I guess. Instead of passing one more bias.
And then how I'll get the right side value, the upper
Again,
limit?
She's calling one more function, right? Can you go for the main function?
No, actually, see, the 8 or whatever the values are, target values can be more than 2, 3, 4, something, right?
Yeah, it can be, yes.
So therefore, in that case, you'll have to go to the extreme left of that or extreme right of that target value, right? And that is what the reason she has to do it very, what you say, she is indexing one by one on line 15 and 17.
Okay, but
so what we need to get the range. So what is the start for that value and what is the end for the end index for that value?
Okay.
So till 12th, when you come inside the 13th loop, it is iterating one by one index, but otherwise it is going binary search. So she is trying to come to the target, focus of our area of interest, and in that she has to do it +1 every time or -1.
No, Santosh, again it will be a binary search.
Yeah.
So just actually, yeah.
It is still a binary search, but if you look at the way we have to compare, because we have to go one by one index, right? Almost. Yeah, it will jump if you have many indexes. Yeah.
No, it will not. It will not go one by one.
It will go to the mid. Yeah.
It will again check the mid.
Yes, it will again check.
So that is what I'm saying. Yeah. But if you have 100 times, it is going to do a binary search in that case.
Yes.
Yes.
It is going to jump. It will be log of n also. Yeah.
Yeah.
But to just make it visualize, it is going one by one. So it is going to the extreme left or extreme right. That is what I'm trying to explain.
So you can say like it will go one by one to the target. You can say the target which we want, we can go by one.
Yeah, first left and then right.
Can you show me the main function, the search range? Okay, so in second search helper, we can do small optimization, right? Because we know the lower bound. So to get the upper bound, we can constrain our search space from lower bound to num -1 or to the size of -1. Actually, I did the same approach, just a small optimization there.
So you're
So
saying
no
instead
need
of
to, yeah, you can also pass the range high and low, because you already know the lower bound and you only interested to upper bound, so you can just restrict the.
But in that
Mhm.
case, we will always moving towards right, so that will not hit.
No.
That lower bound will never hit.
No. Why?
Because we are, she's already moving towards right.
Mm-hmm. So the upper bound would be at the right side, right?
Yes.
So if there is only single element we are looking for, that would be, it will be on the, that means lower bound and upper bound is same point, as it would be somewhere out the right side. So no need to pass the full, or no need to binary search on the full array. I mean, we can just shrink the search space for the second time.
Okay, if you want to go with that, I mean, that's fine.
So you are saying instead of these, including these, I can pass the lower and the higher, like the range thing, to start
Actually,
my binary search in that range.
Actually, Sonia, watch, he's actually trying to handle that. He's trying to handle the case where there is only one element. So in that case, you don't need to make the search again. That's the only case you will get benefit from there.
Even for other elements also, for the second time when we call search helper, we are again looking for the upper bound on complete vector. And we can do better than this because we already know the lower bound.
Yeah, we are already in that space.
Exactly. So I'm just suggesting that no need to call this the second time binary search on the complete vector. Just reduce the search space. That will be your lower bound to the size of vector minus one.
So when I get the return, I'll get the I'll get my starting index that my 8 is starting from this particular index. So I'll start with my lower would be that index, and the higher would be the end of my array.
Correct,
exactly. So you should search. You should do only search between result of 0 and to the size of this vector minus
length.
1.
Yeah, here would be 0 to length minus 1, and then here would be my index to the.
You got me. I mean, I don't.
Yeah, it's another optimization. Yeah, that's
that optimization can be done. Yeah, that's nice.
Good, yeah.
I'll try that. Thank you.
Excuse me. Can you go through the code once?
Hello. Also, I'm just wondering if the less than equals to the low less than equals to high, if that becomes low less than high, line number 9, would that cause any difference?
I sometimes I do these kinds of binary search only every time. Low is less than equal to high.
Yeah, the only difference is there will be one more loop. We are allowing one more loop.
One more loop for when low is equal to high.
Mm-hmm.
Yes.
So then what happens is you'll have to capture the result somewhere, because like if low is less than high, then you exit from it when low is equals to high. That means you can either say either use low or high as the index and return it. But if it is low less than equals to high, then you will have to keep the result somewhere, because of course they are going to run on top of each other, right? So they are going to be either low is becoming greater than high or high is becoming less than low.
I think we should use the equal to, because let's say the target element is at the last position, then I think that this would we would hit this case low equal to high, and she's checking that nums of mid is equal to target. So
when are low and high at the same position?
That is one way to implement the binary search, but in that case, the high what she's actually taking, she's considering that the high is a valid index. So in that case, the high will be nums dot length only.
Yeah. So what I'm saying is that about this condition, low less than equal to high, I think it should be low less than equal to only. So taking an example, if a target element is at the last position, then we need to we need that iteration where low is equal to high, and then mid would be at the last index, and then that is where this condition would be true, line number 12. So if we stop at low less than mid, then suppose we have two indices, 0 and 1, then and our target is at index 1, so our mid would be 0, and then after this we would break, so we would not
Yes.
check that target element.
So for example, over here, 0, 1.
Yeah.
So what I'm saying that is one way to implement the binary search where people consider the high as an invalid index.
Okay.
Yeah, if you search on the lead code and search for the binary, look for the binary search template, so you will see that somebody shows that there are 3 ways to implement. So one way is that where you consider that less than equal to high, and another way is then low is less than high, and the third is low plus 1 less than high.
Yeah, so I'm talking about this code only, what Sonia is written.
Okay.
Okay, so yeah, that's a good thing what you brought, Praveen. So they have clearly differentiated where we have to use those 3. So we have a special cases for using all of them. You said L is less than R, L is less than or equal to R, and L plus 1 is less than R, right?
Yeah, I've seen, but personally, I have not seen any cases. If you know, could you please share that? I mean, where actually one.
No, actually, I'm trying to find out where it's seen there, because I see so many implementations. I'm really not sure where to follow, because what Harshit was explaining, I'm also having the similar questions. And when you try to end up using what is your favorite style, sometimes it doesn't work, So if you really can differentiate where a special thing has to be used, that would be really helpful. You said there is something in the lead code.
Yeah, but personally, so far I have not found any single instance where I follow this template and where it did not work for me.
Oh, okay. Yeah.
So if you have some scenario, could you please share where that a particular template does not work?
Okay.
And that discussion is in the lead code only. What
Yeah, he's saying that. Yeah.
Oh yes.
I will have to find out.
Okay.
Sonia, could you go to the Explorer part and then search for the binary? When you Explorer, the first one. So they have the template.
While he's searching. So did someone try using lower bound and upper bound function?
I think
Lower upper bound, what do you mean?
Shashank's implementation was exactly that, right?
But I think it won't pass all the cases. Like if the element is not there, then lower bound does return me something, right?
It will return the next greater element.
So
yeah, right.
You need to say.
So you want to go for this?
Yeah. You will find the template somewhere here. Yeah, template 1, 2, 3. You see on.
So this is low is less than equal to right?
There's another template too.
Okay. There is so many things in lead code.
Yeah, so yeah, this is left is less than right. Yes.
Yeah.
So yeah, here but over there, it's like you need to go right is like a mid -1 or here left is mid +1. When we are over here, this condition changed.
Yes.
Yeah. Even in left +1 is less than right, you'll have to use a similar type, I would say. why that's
So here they, okay.
oh, they separated here. Okay.
So there is like no +1.
No +1 at all.
+1 or -1, yeah.
Yeah, and still it is working without any DLE. Okay.
Yeah. So yeah, you are right. There are 3 different approaches, but so based on the question, we need to make sure what approach we should be taking so that which template would work best in that question. For example, in rotated or in like finding the square root. So we have different binary search questions, but which template would suit best, that we need to differentiate it. I think so.
I would say, yeah, that is right. But whatever is good for you, you should be able to apply it everywhere, I would say, because in any case, if you find everyone will implement all the templates for each and every question.
And it will be difficult.
Yeah.
And Sonia, so far, I mean, I have not seen a single instance where I was not able to solve a problem using template one.
Okay, but no, I have like
I don't know. I mean, what is the criteria to determine which one is the best one or the correct one?
Only one thing, if you see for the lower bound and upper bound, you know, what we have in C++, if we try to implement that, okay, don't use lower bound and upper bound, which are the STL part. But we try to implement exactly that, then I think you'll have to follow only a single template, I would say. Because I think there is some tricky thing in that. So you can't use all the 3.
But sometimes I think when we need to make our array biased one, like we are forcing it to make it biased, then we don't there in that questions I don't use the first template. Like,
in fact, I like your solution for that, the bias way what you did, the lower index and upper index. It is slightly easier to remember also.
Yeah, exactly.
Yeah.
Okay. Shall I go to the?
Yeah, sure. Yeah, Shashank, can you bring up your code? We just the last thing what we wanted to discuss on it.
Yeah. So which area, like, I mean,
Someone had that on line 5, right?
Yeah, this one.
Yeah, so you're saying that if the element is not there.
9 is not there, right?
Yeah, so 9 is not there, right? So how are you proceeding for that?
So if 9 is not there, it will, I mean, it will just try to, what would be the possible index for 9?
Okay.
It will be 10, right? Yeah.
Yeah, it will be 10.
Yeah.
So this, so last index would be the index of 10, right?
Exactly. Yeah.
And what about line number 4 when you try to find out the left occurrence?
Line number, first we'll go for this only.
Yeah, so that would return.
Check that if first index is less than last index, then only you need to perform both this way.
Okay.
Yeah, that will take care of. You're getting confused that, I mean,
yeah, I thought it should return -1. I mean, I didn't focus on this. Sorry, my bad.
No, it's
okay, so that slightly different way you are taking care of the last index here. Okay.
Yeah.
This is, I mean, this is taking care of.
Okay.
Yeah, I think this would also be used if I try to implement by that lower bound and the upper bound C++ STLs.
Yeah, makes sense. Yeah, maybe.
Yeah.
Lower bound and upper bound, right?
Because if suppose the element is not there in the array, then the lower bound function does return me some index. So lower bound is the first element not lesser than that element, right? So it would return me some index, and similarly for upper bound, even if it's not there. So that would give me some answer, but it should be ideally -1, -1. So I'll have to do this check. Line number 6.
So lower bound and upper bound, actually they will return a value exactly the target or greater than that. But only difference between lower bound and upper bound is what I found as upper bound won't return the target if the target is present, but it will return the next greater element. But for the lower bound, if it finds the target, it will return the target. Or if it doesn't find the target, then it will return the next greater one. Correct?
Yeah.
That's
Yeah.
the only two.
So this is the same thing then, upper and lower bound concept only. The one in chart.
Yeah. But that C++ is slightly different. Yeah.
I mean, he's doing the same thing. The second call is returning the upper bound.
Exactly. Yeah.
And so the first one also. First one is lower bound. So if it does not find the target, it returns the next element.
Yeah.
Right.
Okay. That's great. Thank you.
Yeah. Thank you.
Thank you, Shang. Thank you. Thank you for your question. Yeah.
Thanks, guys.